Good day, ladies and gentlemen. Welcome to another edition of Prometheus University. My name is Ogiamien. In this part, which is part 8 in our 9-part series on bending stress analysis and design, we will be introducing you to composite beams. The main concept to come from this will be the concept of the transformed section. We'll talk about what that is, and we will determine some pertinent cross-sectional properties of this transformed section with a view to finding flexural stresses in the elastic range. So similar to our first video where we came up with the section modulus MC over I, and our fourth video for plastic section modulus, or video number 7 with reinforced concrete beams. So the idea here is to get parameters, get properties of the cross section with which we can analyze the flexural stresses in the elastic range. We will take the opportunity to elaborate on the neutral axis, a concept which has been taken for granted in our videos so far, by introducing the idea of the moment of area, right? And we will also introduce the parallel axis theorem as a means of determining the second moment of area, which is the moment of inertia. Now, I would advise you to watch the second video over again to refresh yourself with the concept of the moment of inertia, or at least state here that knowledge of the contents of that video are assumed in this video. Okay? In the next video, we will consider the analysis and design of composite beams, the considerations taken for the analysis and design of composite beams more rigorously. But in this video, we'll be looking at composite beams from a conceptual point of view to try to understand the behavior of the cross-section. Composite beams come in different forms, but are generally made with structural steel sections and reinforced concrete. They initially started out from the practice of encasing steel beams in concrete as a means of fire protection, but as lighter and better technologies have come out for fire protection of beams, this is not practiced so much. But back then, right, while the steel was encased in the concrete, the steel beams was encased in the concrete, the thinking was, well, since we have the concrete there, we might as well take advantage of the concrete in the analysis and consider the concrete and its contributions to the strength of the floor in general. The particular kind of composite beam construction that we'll be looking at today is one that is a common method of construction for multi-story steel structures, and it is made with concrete over metal pan decks, below which we have steel beams. Now let's consider the diagram that we have here. This is a side view, an elevation view of a composite beam. The blue portion below represents the structural steel beam, which is a W shape, and we'll see that in a second when we look at the cross section. And we have the concrete sitting on top of that. The concrete has the egg carton shape, if you will, because it's sitting on top metal pan deck, a metal pan deck, corrugated metal pan deck. If you're not familiar with this kind of construction, I would advise you to do a quick search on the internet for metal pan deck constructions, concrete over metal pan deck, to get the visuals and some general aspects of the means and methods associated with this kind of construction. Now, in order to achieve full composite behavior, the steel and the concrete need to be connected by some means. So slippage between the concrete and the steel needs to be prevented, and this is achieved in this kind of construction through welded studs. There are studs that are connected through the metal pan deck and welded directly to the beam, and the concrete is poured on top of that so that the studs are cast into the concrete. This then helps the transfer of the horizontal shear forces. Let's assume full composite behavior in this case, because in our next video we're going to get into design considerations having to do with how many studs you put in and what the limiting factor is. Is it the strength of the steel, the yielding of the steel, or the shearing of the studs, or is it the compressive strength of the concrete? We'll get into all that more elaborately in our next video. But for now, we're going to assume full composite behavior and analyze the cross-section in terms of bending, strains, and stresses in the elastic range. Now, this is a procedure that we are familiar with by now. We're going to look at the cross-section, let's say section XX, and we have there a W-shaped beam, a wide flange beam. And then we have the concrete shown. Notice that we're only showing the top part of the concrete deck, the top part of the fluted metal pan deck. And the reason for that is because that'll be the weakest point in the concrete. Now, we have the neutral axis represented here by the green line as usual. And we're going to draw our experimentally verified strain diagram. The strain diagram is linear. The linear smooth transition from the compression zone on the top to the tension zone below. Now we can write here that in the elastic range, the stresses, right, the flexural stresses is equal to the moment divided by the section modulus, or MC over I. Now at this point, we would want to go forward and draw our stress diagram. And in the elastic range, we're seeing here an experimentally verifiable strain distribution that is linear transition from tension to the compression zone. So we would expect a linear stress diagram. However, we're dealing with two different materials that have two different stress-strain relationships, two different numbers, the elastic modulus, that represents their behavior in terms of stress and strain. Their stiffnesses. It turns out that steel is a lot stiffer than concrete. So for a given strain value, steel will be experiencing a whole lot more stress because it takes a whole lot more stress to strain steel that equal amount that you're straining the concrete. The concrete will have less stress than the steel. Well, let's take a step back and go back to our stress-strain curve and talk a minute about the elastic modulus. We have here the curve that we're quite familiar with by now. On the horizontal axis, we have strain, and on the vertical axis, we have stress. The blue line represents the stress-strain curve, stress-strain relationship from which we get the elastic modulus for steel, and the red line represents that for concrete. We notice that steel has a much steeper curve than concrete. That's because it is stiffer. It takes a lot more stress to deform steel than it does to deform concrete. So at a particular strain, right, at a particular strain, which let's say we represent by this vertical line on our curve, the steel is experiencing a certain stress while the concrete is experiencing a much lower stress, right? What is the difference between these two? Well, for about 3,000 psi concrete, right, the difference between the elastic modulus of steel and the concrete is 9 times. The steel is 9 times stiffer than the concrete, okay? So let's investigate this further. Let's start by looking at the stress distribution following the strain distribution with the steel. So we see a linear distribution of stresses going from the tension zone into the compression zone, and we would expect it to continue in that manner shown here, the stress diagram, this straight line going up, if it was a homogeneous material. However, it is not homogeneous, and concrete, being less stiff, will have a different stress response to the strain that has been introduced. It will have less stress, right? Because it is less stiff, okay? So it'll have a stress curve that looks like this. Now, our linear MC over I equation with which we calculate stresses, flexural stresses in the elastic range, is no longer valid. There's a discontinuity here. How do we resolve that? Well, it turns out that in order for our elastic flexural stress equation to be valid, we must transform the section to an equivalent homogeneous section, a section that is equivalent in terms of stiffness. Now, the way that we do that is we transform the concrete into an equivalent amount of steel. So let's look at the concrete. Let's put some dimensional parameters to it. It's 6 inches thick and 36 inches wide. Now, how do we determine the width of the concrete in this floor system? How do we say, well, 36 inches is the compressive portion that is contributing to the beam? How do we come up with that number? Well, we'll see in our next video how the effective width, right, of our concrete is selected from the floor slab. But for now, we just go ahead and put a number to it, 36 inches and 6 inches thick. In order to create an equivalent cross-section, we reduce the area by 9 times. We reduce the area of the concrete by 9 times to create an equivalent steel section. In other words, it takes 9 times less steel to do the same work that the concrete is doing, because steel is 9 times stiffer. Now, concurrently, the stresses in the steel goes up, but the strain stays the same, the deformation stays the same, because we have a stiffer material. And now our stress curve becomes linear and it follows the strain curve. And we can now manipulate this cross section and use our elastic range flexural stress formula, MC over I. What we need to do next is to locate the neutral axis of this new cross section, find the moment of inertia of this new cross section, and then use this flexural stress equation to find the stresses at any location along the cross section. So just to take a step back, we had a concrete and steel section. This makes it such that our linear flexural stress equation is not valid. In order to make it valid, we create a transformed section that is made from a homogeneous material. We change the entire material to steel. We create an equivalent amount of steel from the concrete. There is a relationship of 9 times between the stiffness of steel and the stiffness of concrete. We reduce the area of the concrete to an equivalent amount of steel. The stresses go up, but the strain remains the same. Now we have a homogeneous material for which our flexural stress equation is valid. Let's define some more parameters of this cross section. The beam which we've been looking at, let's say it's a W24 by 104, a wide flange beam, 24 by 104, which means, by the way, that it's 24 inches deep nominally and 104 pounds per foot. That's what that nomenclature means. We can get cross-sectional properties from our steel design manual tables for this particular cross-section. It is a defined cross-section. It has 30.6 square inches of area, and we can get its moment of inertia, and as far as its neutral axis, which is the same as its center in the elastic range. So the center or the centroid of a shape is the same as the location of its neutral axis in the elastic range. That we can intuitively determine. Halfway between its 24-inch depth, so 12 inches along the vertical, right in the middle of the web is going to be its center of gravity, if you will. Now the question is, what is the center of the composite shape? What is the neutral axis of the composite shape of the wide flange beam plus the equivalent steel section which we created from the concrete, which again is 4 inches wide, 6 inches deep. There's a 3-inch gap between the bottom of that section and the top of the wide flange section, and that is basically the depth of the bottom flute of our corrugated metal pan deck. Now let's talk about this idea of centers. Now we're looking for the center of this arrangement of area. We have a visual intuition for the center via symmetry. And the center of an area corresponds to the center of a mass in an even distribution of masses. So for example, the center of gravity of a disk of uniform mass and thickness is the same as its visual center. Its visual center we have an intuition for via symmetry of visual intuition, and for even mass distribution it is the same as its visual center. The center of area also corresponds to the center of an even stress distribution. So if you have an even stress distribution over an area, the center of that area is also the center of that stress distribution. In video 2, right, where we came up with the mass moment of inertia and then related to the area moment of inertia, we saw this dance between mass and energy quantities on the one hand and spatial and geometric quantities on the other. We saw the dance from the mass moment of inertia to the area moment of inertia. This kind of analogy making is common in Newtonian mechanics. For example, the dance between kinetics and kinematics. We have mass and velocity and forces on one side, and you have spatial quantities on the other hand. This is a concept that we're also going to employ in order to determine the center of an area where we do not have complete visual intuition, right? We can tell that the center of this composite shape is going to be somewhere above the center of the wide flange shape. And that's because we added some area to the top of the wide flange shape. Therefore, we're going to move the center of mass accordingly. Now, what we're going to do here is we're going to treat the area like an even distribution of masses or an even distribution of stresses and employ a concept called the moment of area, a rotational force concept, in order to find the balance point or the neutral axis or the centroid, the center of mass, center of gravity of this arrangement of area. We establish a datum, and as we stated, we say that the first moment of area helps us to find the neutral axis of a composite shape with respect to our datum. And the way the process goes is as follows. We state that the distance from the datum to the center of gravity of this distribution, let's call that C, the distance from the datum here, the datum line on top right there, to the neutral axis represented by that green line there, is C. So that distance multiplied by the area of the distribution, the total area of the wide flange and the rectangle, gives us a moment. So if this was a distribution of masses or a distribution of stresses, the distance from that datum line to the center of gravity of the distribution times the total magnitude of the distribution itself gives us a moment. Now, from Newtonian mechanics and statics in particular, we know that the moment we just defined is also equivalent to the moment that can be obtained by multiplying the individual areas, that's the rectangle and the wide flange, by the distances from the datum to their respective centers of masses. So let me go ahead and state that formally. Our first statement is that the moment from the datum is equal to the entire area, that is 30.6 square inches plus 24 square inches, times C, the distance from the datum to the neutral axis. At this point, we don't know that. It's an unknown quantity. Next, we write down the expression for the moment of area relative to the datum line for the individual components of the composite area. So we say 30.6 square inches, which is the area of the wide flange beam, times 21 inches, which is the distance from the datum line to the center of the wide flange beam, plus 24 square inches, which is the area of the rectangle, multiplied by 3, which is the distance from the datum to the center of the rectangle, is equal to 714.6 cubic inches. 714.6 cubic inches is the moment of area of the composite area relative to the datum line. So if we substitute that number for our moment in the first equation, we can find C, right? By simply rearranging the equation, we find that C is equal to 13.6 10.1 inches. And this is how we find distance to the neutral axis using the concept of moment of area. Next, we need to find the other parameter in our elastic range stress formula, the moment of inertia, the second moment of area, right? We already found, using the first moment of area, the neutral axis. Now we need to find the second moment of area of this composite shape. It is basically a measure of how much energy it takes this composite shape to rotate about its neutral axis, which we just found. We will do this by introducing the parallel axis theorem. The parallel axis theorem allows us to find the moment of inertia of a composite shape. It is a way of operationalizing the calculation of moment of inertia in a particular situation. And the situation is as follows. I'm trying to find the moment of inertia about the neutral axis of this composite shape. I have the moment of inertia of the individual components of the composite shape about their neutral axis. The neutral axis of the individual shapes for which I have the moment of inertia is parallel to the new neutral axis of the composite shape. When you have parallel axes, such as the ones we see here, that of the individual shapes shown in blue, as blue lines, and the neutral axis of the composite shape is the green dotted line. When we have a situation like this, the parallel axis theorem can be deployed. However, the parallel axis theorem does not add anything new to the definition of the moment of inertia. It comes directly from the definition of the moment of inertia. It is simply a way of performing a calculation. So if we recall, the moment of inertia is the integral of r squared dA. If we consider dA to be the individual masses in this case, so the individual areas in this case, we go from mass to area as we know when we derived the moment of inertia. If we consider the individual areas to be the dA value, the r value is the distance from the center of these individual areas to the axis of rotation. Just like we did when we defined the moment of inertia and derived the moment of inertia. So let's call the rectangle area 1 and the wide flange area 2. And we have distance from the center of area 1 to the neutral axis of the composite shape is 10.1 inches. And the distance from the center of area 2, the wide flange, to the neutral axis of the composite shape is 7.9 inches. Now, we know that in order to find the moment of inertia, we simply need to multiply the area times the square of the distance from that area to the axis of rotation. So we can simply do that. We say A1 times 10.1 inches squared plus A2 times 7.9 inches squared. However, A1 and A2 have an individual moment of inertia. They're not points. They're not points in space or point masses. They have extension, and they have a moment of inertia as well about their own axis. For this composite shape to rotate in and out of the page about the neutral axis, it not only needs to rotate about the neutral axis, but each of the composite areas needs to rotate about their own centroidal axis. So there's an energy associated with that, a moment of inertia associated with that, which we can determine by integrating, but which we already know for these common shapes. So what we need to do is then add the moment of inertia of shape 1, which we can determine, which we derived in video 2, and the moment of inertia of shape 2, which we can look up in our steel design tables. And what I just did is the parallel axis theorem. The parallel axis theorem says add the moment of inertia of the individual components and then multiply the area times the square of the distance from the center of each area to the axis of rotation, just in the same way that the moment of inertia definition tells you to. So hopefully you can see intuitively why this is true. why in finding the moment of inertia of a composite shape, you take each individual area, you multiply that area by a square of the distance from that area to the axis of rotation, and then you add the individual contribution of the moment of inertia of the area itself to the part to get the total moment of inertia of the composite shape. This, which I just described, is the parallel axis theorem. Now let's do a quick recap. This video was relatively long, but as I mentioned in the beginning, the main concept to come out of this is the concept of the transformed section, which was the idea of coming up with an equivalent section of a homogeneous material for a cross-section that is made of two different materials that vary in terms of their stiffness. So we had concrete and steel, but what we did is we created an equivalent homogeneous cross-section with all steel by creating an equivalent area of steel that represents the same area as the concrete that we had. When we do so, our elastic flexural stress equation becomes valid. We then came up with the transformed section that we needed to find cross-sectional parameters for in order to solve for elastic stresses, flexural stresses in the elastic range, I mean. So we needed to find the neutral axis and the moment of inertia about that neutral axis. And with these parameters, we can then define the stresses at the top of the steel or the bottom of the concrete or the top of the concrete. If we find the stresses in the equivalent steel section, we would need to divide those by 9 in order to reduce them to the equivalent amount of stress that will be on the concrete. Thank you very much, ladies and gentlemen, for listening to another edition of Prometheus University. In the next video, we will be continuing our journey into composite beams. We will more rigorously consider design and analysis considerations such as the limiting factors like the shear strength of the studs that connect the steel to the concrete, or the crushing of the concrete being a limiting factor versus steel being a limiting factor, and go through the design process of a typical composite beam structure. If you enjoyed this video, please subscribe to our page, share, like, ask questions. Next, after our bending stress series, we'll be coming out with a series on structural dynamics and also on shear and torsion. So feel free to leave us comments on other series and topics that you would want us to cover. Thank you very much. Bye.